Okay, so first of all, thank you very much for inviting me. And my name is Guillermo Blanc. I'm a staff astronomer at the Carnegie Observatories. I also hold an adjunct position at the University of Chile. And I started my career as an astronomer when I was a student studying high redshift galaxies, Lyman alpha meters at redshift 3 and so on and so forth. And I've been slowly moving towards lower and lower redshifts until I reached the Milky Way, recently. And I think this, it mostly reflects, a desire to try to understand really what's happening inside galaxies in terms of physics, which is very hard when you don't have spatially resolved measurements of the ISM and the stellar populations and the star formation that is happening in them. Really, this talk is far from being a complete review of ISM and star formation and what we know that would be impossible to do in 20 minutes. There are many things I will not talk about, like, I don't know, AGN feedback or quenching or chemical enrichment, etc. But it's really more of a list of things I wish I knew when I was a young student, observing high redshift galaxies to better understand the physical context in which star formation is proceeding. So I'll start by making a point that is that star formation and feedback are at the core of the physics that gives rise to basically all the galaxy scaling relationships that we all know and love and that we measure throughout the history of the universe, right? So things like the cosmic ray, the star formation rate, cosmic density, or the galaxy stellar mass function are modulated by the processes, the physical process that drive star formation. We think that, for example, feedback, at low halo masses from stars, and feedback from AGN and high halo masses, is what makes this stellar mass function different from the dark matter halo mass function. Things like the mass metallicity relationship, how the chemical enrichment of galaxies proceeds and increases over time, and its mass dependent is fully driven by the process of star formation and how chemical elements that are produced in stars are, then dispersed and mixed in the ISM. Things like the star formation main sequence, or stellar mass star formation relation and quenching are fully driven by star formation. So it's fundamental in order to understand galaxy evolution, to understand how star formation proceeds in the ISM. And the reason star formation and feedback are so important is that massive stars, young massive stars in young star forming regions are the main energy source in the ISM, for the ISM of galaxies. What you're seeing here is a pie chart showing the distribution of different energy sources in the ISM of the Milky Way, for example. And you can see that massive stars, feedback from massive stars, supernovae explosions, stellar winds, radiation, ionization, etc., is really what drives the production of cosmic rays, the heating of dust, starlight, ionization, of course, the thermal energy in the ISM is also an important component, and of course turbulence. We know the ISM is highly turbulent, and feedback from massive stars is very important in terms of injecting turbulence into the ISM. So understanding that, you can understand that star formation really sets the thermodynamics of the ISM. It sets its structure and kinematics via feedback and self-regulation, and it also sets the chemistry of the ISM via chemical enrichment. So therefore, these processes are really what are regulating the growth of galaxies throughout cosmic time. And an important realization to have is that star formation is a multi-scale process that happens over 12 orders of magnitude in spatial scales, from the accretion of intergalactic gas on megaparsec scales onto dark matter halos and their centers where the ISM of galaxies are, to the settling of diffuse H1 gas, in disks, where eventually gas can cool down all the way from these kiloparsec scales to the tens of parsec scales, where it can become self-shielded from the interstellar UV radiation field and allow the formation of molecular hydrogen and giant molecular clouds, to the internal structure of these giant molecular clouds, which is highly chaotic and filamentary and turbulent, to the tenth of a parsec scales of dense filaments and cores where gravitational stability can actually occur and stars can collapse and form, to the actual scales or AU scales of, or smaller than, of massive stars that actually inject feedback that can propagate at all these scales in order to regulate the formation of molecular gas, in order to regulate the thermodynamical structure of H1 disks, and also to regulate the way gas accretion happens through galactic winds. So this is understanding star formation requires observations across many different scales, across many different wavelengths, because you need to observe things from all the way from the UV, where you can see massive stars, to submillimeter and radio wavelengths, where you can see the gas, all the way to X-rays, maybe, where you can see the hot gas in dark matter halos. And it requires this huge dynamic range from observing full systems, full galaxies, and samples of representative galaxies with different conditions to the very, very small scales. So let's start by looking into some very basic questions. One is, where does gas come from in the local universe? Okay, so in the local universe, we know that the cosmic ray density in the universe has been dropping by an order of magnitude, since the cosmic noon around redshift 2 until today. And this is largely caused by a drop in the baryon accretion onto dark matter halos. What you're seeing in the right is, I want you to focus on this black line. This is a hydrodynamical cosmological simulation tracing the accretion of baryons into dark matter halos, in this case, massive halos or Milky Way-sized halos. And you can see that it drops by about a factor of 10, right? So the way gas accretion happens in galaxies today is very different than the way it happened in the past. And in fact, when we think of gas accretion at high redshift, we think of this cold mode and hot mode of gas accretion, where some gas comes in, gets shocked to the virial temperature of the halo, and then cools down, while other gas, this cold mode, you have gas that is colder and can funnel all the way through filaments into the ISM. But really, at low redshift, those modes are highly suppressed because this very low accretion rate from baryons, and what dominates is recycled gas from the galaxy itself. Okay, so we're seeing here in the right, these green curves here as a function of redshift show the accretion rate from this wind mode or fountain mode, where you have gas that's expelled from the galaxy, it mixes, cools with gas in the circumgalactic medium and rains back onto the ISM. So it has important implications. The main source of fuel or gas at redshift 0 is reprocessed material that's already chemically enriched and comes out of the ISM and back to the ISM. Okay? Now, when we think of within galaxies, within star-forming disks in the local universe, where do stars form, right? We immediately should think of the fact that we know that there's a correlation. We have known for decades now, there's a correlation between the presence of gas and star formation rate, right? This is the famous Schmidt-Kennigan law. When you look at the Schmidt-Kennigan law on spatial result scales, on let's say sub-kiloparsec scales inside galaxies, you can actually start, dissecting this a little further and understand what phases of the ISM are the ones that correlate with the star formation rate surface density. And what you're seeing here is work by Shruba et al. From the Heracles survey, almost 10 years old now. But what you see here is that there's clear evidence that it is molecular gas, H2, and not atomic gas that correlates with star formation, okay? And that the relations that we see with this fall at low surface density when we look at the total gas are driven here by basically the formation of molecular gas, in the ISM. And this is basically a density threshold for H1 to become self-shielded and allow the formation of molecular gas. So when we think of where, spatially inside galaxies, star formation is happening, the answer is really everywhere where molecular gas can accumulate. We have this idea in our minds, at least I had until very recently, that really star formation is highly concentrated in spiral arms, in the centers of galaxies, in nuclear starburst rings, etc. But when these are results from a recently submitted study using data from the Fanx survey, looking at a large sample or representative sample of galaxies observed with ALMA and other facilities. And you see here a histogram of a distribution of molecular gas and star formation. And you see that centers, bars, spiral arms, interarm regions, they basically account for similar fractions of the total star formation rate and molecular gas fraction within galaxies. Of course, they have surface densities that are very different because they have areas in the galaxies that are very different. You have a lot of area in internal regions. Centers are very small. And you can see this here, right? This is the distribution of molecular gas surface density, where the centers of galaxies can be up to 10 times denser than spiral arms. And spiral arms are, of course, denser than internal regions. And you see this again in star formation. But really, in terms of relative contribution, these environments contribute fairly similarly, and that's very interesting. And also interesting is that the depletion time, that is the time that it would take for all this gas to be consumed, this molecular gas to be consumed, if the star formation rate proceeds at the same rate, it changes only very modestly between environments, which doesn't necessarily mean that the star formation efficiency is different, okay? One point I want to make is that we have Schmidt-Kennigan laws, or correlations between gas density, gas surface density, and star formation rate surface density, from integrated measurements of galaxies all the way to scales of sub-kiloparsecs. But as soon as you get to scales closer to 100 parsecs, the scatter in these relationships blow up. The central plot you're seeing here shows the scatter in the Schmidt-Kennigan law as a function of spatial scale, all the way from several kiloparsecs to a few hundred parsecs. And you see how that it blows up. So these correlations eventually disappear as you start resolving the time evolution of star-forming regions. When you look close enough, you have a GMC here, an H2 region here, a young cluster over there, and things are not correlated anymore. And only when you get to the scales of the internal structure of GMCs, like tenths of a parsec scales, you start seeing young stellar objects correlating with dense gas inside giant molecular clouds. And you have a sort of molecular cloud Schmidt-Kennigan law arising again. Okay, so this is a very important thing to understand results that you see in the literature at different resolutions. Okay? So a fundamental question is, what sets the efficiency with which stars form inside giant molecular clouds? Okay, and the theoretical framework in which I think most of us are thinking about this these days relates to, it's observationally motivated, and it relates to the shape of the gas density PDF, the probability distribution of the gas density of molecular gas inside giant molecular clouds. So this is showing data from this is showing the extinction map of the Taurus giant molecular cloud in the Milky Way, and you can see that there is a log normal PDF density PDF followed by a power law at high densities, right? And basically you expect to see this log normal PDF because the density distribution inside molecular clouds comes from shock compression and the stochastic accumulation of the compression from different shocks, which is a multiplicative effect that should translate into a log normal density distribution. And this power law tail is thought to be related to the collapse of gas, where there is some critical density above which gravity can actually overcome the sources of support in molecular gas, that is thermal pressure, turbulent pressure, magnetic fields, etc., and can actually drive gravitational collapse, produce this high density power law and form stars. Okay, and there's a plethora of theoretical models out there, trying to say, what are the relevant physical mechanisms and how can you parameterize them to establish the shape of this PDF, the density corresponding to this critical density, and how this high density power law behaves. And they all have their difference, and they have different physics, etc. But there's some commonality to all of them that I think is kind of a general realization now. That is that, of course, the relative, what you're seeing here in these plots, this from Federath and Klesen, is the star formation rate per freefall time, how much gas forms into stars per freefall time, versus the virial parameter and the Mach number for different theoretical models, okay? And what you see is that the relative strength of gravity versus turbulence, of course, is very important to set the star formation rate, okay? So high virial parameters means a lot of kinetic energy with respect to gravitational potential energy. So you have support, basically, against gravity, and star formation drops if the virial parameter becomes much higher than unity. But interestingly, also the Mach number seems to be very important. This is the relative energy in turbulence versus thermal energy, right? And really, and what happens here is that at high Mach number, at high turbulence, that you might think would provide support, you have very efficient star formation. This is because shocks, turbulent shocks, is what provides compression to form dense gas. Okay, and an important realization here is that, so we just learned that the internal properties, the internal physics inside clouds, turbulence, gravity, thermal, etc., are basically affecting star formation efficiency. So this means that the overall properties of giant molecular clouds affect the efficiency with which star formation proceeds inside them. And if environment can affect giant molecular clouds, then you expect environment to also affect the efficiency with which star formation can proceed. Here I'm just showing you results from Sandoval 2020 in a very nice paper that shows that giant molecular clouds are in pressure balance with their diffuse ISM, around them, when you consider also their self-gravity and the turbulent pressure within them. They're basically balanced. And this implies that environment, can have an effect on the internal properties of giant molecular clouds and the star formation efficiency. Here, I want to focus on the bottom plot here from Leroy et al. 2017. There's a study where we managed to measure the star formation efficiency per freefall time in the ISM of M51. And you see correlations with environment, with local quantities like the local molecular gas surface density or the local molecular gas velocity dispersion. And we're just starting to scratch the surface observationally of, how do we test and corroborate all these different theoretical models of star formation and how it proceeds. And the reason we're just starting is because this requires, as I said, multi-wavelength data sets across many wavelengths, across a huge dynamic range in resolution, right? So these data sets are super expensive. So I want to, play this video about a project that's called Fanx. You might have heard of it. The focus of Fanx is to study the life cycle of baryons in the ISM of nearby galaxies and study this, transition from atomic gas to molecular clouds to the formation of young stars in the ISM of nearby galaxies, and the feedback that these young stars produce on their environment, both through ionization and supernova explosions, etc. And this requires massive amounts of data, right? So it required a huge collaboration to pull together, ground-based radio interferometry with ground-based optical spectroscopy, with space-based satellite imagery from ALMA, MUSE, HST, and most recently JWST. We just got a program approved on JWST, which is very exciting. So we have an ALMA large program to map CO over 74 nearby galaxies. We have this ESO large program to map, get optical IFU spectroscopy for a subset of these systems. And we also had 120 orbits of HST time to get UV optical imaging across, again, a subsample of these objects. And it's really when you combine all this data, from across many wavelengths and going from whole galaxies to very small scales, that you can start getting a clearer picture of how star formation is proceeding. To finish, I just want to mention also another project is called the SDSS-5 Local Volume Mapper. You might have heard of it. And the only point I want to do here is that, what you're seeing here is a patch of the large magnetic cloud at 100 parsecs per pixel all the way to 1.6 parsecs per pixel. Like with Fanx, with ALMA, with MUSE in nearby galaxies, we can only get down to these scales where you can simply identify that there's a single star forming region there. You can separate it from its neighbors. But it's really only when you get to these tens of parsecs to parsec scales that you start resolving all the filaments, the shocks, and the internal structure of H2 regions. So this is basically what we're doing with the local volume mapper. This is an IFU survey of the Milky Way and the large and small magnetic clouds with sub-parsec to 10 parsec resolution, right? It's something that we call the Spectral Panopticon. This is just to show you what the footprint of this project, this survey will be on the Milky Way disks, Orion, and the magnetic clouds. And just to get an idea of how this IFU will work, it will have 1,800 fibers spread over a field of view that's roughly the size of the Milky Way. So you have 30 arcsecond spaxels that when you use them to map the Milky Way disk, you can sample, the ISM at extremely fine grade, basically. And we really hope that pushing these projects towards very high resolution over very large and diverse set of environments is going to allow us to learn more about star formation. So the take-home message for the talk is we can map the whole universe with our beautiful, massive spectroscopic facilities. And don't get me wrong, I love those facilities. I'm working on designing one. But we're never going to understand galaxy evolution until we understand star formation and feedback. So you can travel around the world. You can send your Magellans to sail around the world and draw maps and stuff. But until you send your Humboldts and your Darwins to get off the ship and like start collecting bugs and looking them at under a microscope, you will have these huge gaps in understanding and knowledge. And these things look to me very much like sub-resolution prescriptions for numerical simulations, right? So it's really important to peers at high resolution into nearby galaxies to understand galaxy evolution overall. And that's all. Thanks.